So, good morning to those of you on the West Coast, good afternoon to those of you joining from the East Coast, and good evening to anyone joining us from Europe or stations further east. Thank you for joining this, the third of our regular series of short courses on pumping topics. This will last about 30 minutes, allowing us plenty of time for a Q&A session after the presentation. Those of you who attended one or both of the earlier sessions will know that we are deliberately steering away from product presentations and towards educational content, addressing a pumping topic in each one. We believe this is very important at a time like this in the new world order, where many of you engineers are working from home, which makes in-workplace training that much more difficult. But having said that, please forgive me 4 or 5 brief slides to remind you of who we are and what we do. We are Real Pumpin'. We are now truly a global company, a big player in the market now. With over 70 years of experience, manufacturing facilities in 10 countries, and over 70,000 pumps installed worldwide. Manufacturing plants in 5 continents, 1, 2, 3, 4, 5, and manufacturing plants in all these countries. We are in all the industries that you guys are in: power, water, chemical, industrial, and oil and gas, most important probably. We've divided ourselves into 5 product lines, 5 divisions: API and process pumps, industrial and standard pumps, fire systems, decoking systems, and we are one of very few pump companies still to own our own foundry, which gives us full control over the manufacturing from beginning to end. We have a huge range of products, from single-stage overhung pumps, foot-mounted or Santaline, ANSI, ISO, general purpose, or API 610. Between bearings pumps, axially or radially split, again, API 610. Horizontal multi-stage pumps, axially split case and radially split case double case pumps. Big range of vertical pumps, both single stage and multi-stage, radially double case and single case, and indeed submersible pumps as well, submersible motor-driven pumps. We also manufacture a range of positive displacement pumps. We have magnetic drive pumps and package systems and fire systems. I've added a few slides at the end of this presentation as an appendix, showing the full range of our products. But I don't plan to spend any time on them now. You can take a look at your leisure when you get a copy of this session. So that's the end of the commercial. Now back to the subject matter. This seminar is going to look at system curves, pump curves, how they interact, and how they impact pump selection and successful operation in the field. We will be holding a Q&A session at the end of this session. Now, as you know, it's a Zoom session, and with as many people on board as we are now, which is 133, it makes it impossible to have a fully interactive Zoom session or Q&A session. But we'll do the best we can. And those questions that I can't answer in the limited time available at the end of this presentation, we'll handle over the next few days Please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the meeting, and the rest we'll do later. We are recording this session, and we will make it available as a YouTube video, and also a copy of the slideshow, a PDF copy of this slideshow will be made available to you at the end of the meeting. So, system curves. The system curve has three components. Static lift, you're pumping from elevation A to elevation B. So that's the static lift. The system required pressure, well, that's the pressure your process needs after we've pumped it from A to B. And the friction losses in the pipework, getting it from A to B. And that gives us the system curve shown here in green, the total system head curve. We superimpose the pump performance curve on that. And there is your nominal duty point. This is a generic system curve, and indeed it's a generic pump curve. We'll be looking at the different shapes of system curves and the different shapes of pump curve. So the system curve first. This can be either mostly friction, as shown here in green. It can be mostly static with very little friction, as shown here in purple, or something in between, as shown in yellow. The mostly friction curve is by far the most common. Now, in the next few slides, we'll look at the various pump curve shapes. Curve shape is a function of the specific speed of the pump. Here is a definition of specific speed. You can consider it to be a dimensionless number, except that it isn't actually dimensionless. You get a different number depending on the units you use. It's most commonly referenced in US units, as here at the top of the slide, and that seems to be the case all over the world. However, if you want to know what it is in metric units, here are some conversions into two of the more common metric versions of the specific speed. I'm now going to show you 5 different curve shapes. The first will be for a specific speed of around 500. Now, these impellers are low flow, high head, frequently used on small pumps, 1 inch, 2 inch, 3 inch pump discharge sizes. They have a fairly flat curve, 10 to 15% head rise to shutoff. And occasionally they might have a slight hook, especially if they're at the bottom end of this range, the 500 range. Don't let this hook worry you. I will address it later. It's not something that is of any concern. Power curve, continuously rising from left to right. Second is in the region of specific speed, 1,000 to 2,000. So here. Most process pumps fall within this range. Head rise is typically 120 to 140%, And again, we have a continuously rising power curve. The third one is in the region of 2,000 to 4,000, the so-called Francis vane area. A lot of vertical turbine pumps fall in this range. So that's your VS1 and VS6 pumps. Head rise is about 140 to 160%. And your power curve is what is called non-overloading. It peaks at about best efficiency point and falls off either side of it. Finally, the range of 4,000 to 6,000. This range, mixed flow pumps, very much large vertical pumps. Head rise is now about twice that at best efficiency point, and the power also increases towards shutoff. And the final one that we'll be showing you is this axial flow pumps in the region of 6,000 to 10,000 US units. Very high flows, very low heads. Typically used lifting water out of reservoirs. Flow rates in the region of, could be as high as 300 to 400,000 gallons per minute. It's this type of pump. And here's a picture of one coming out of our factory gate. And here's an axial flow impeller. It's rather beautiful, isn't it? These pumps have a characteristic saddle in both the head curve and in the power curve. In practice, you would never be operating in these ranges. You would always be operating around here at best efficiency point for big pumps like this. I'll address this a little bit later on. So that's the 5 curves, shapes. So this is what we're going to consider next, operating bands or ranges. When you give us a data sheet, we would normally see a maximum suction pressure and a minimum suction pressure. So that immediately gives us a band of operation for our pumps. In addition to which, you will have a high flow condition, probably your rated condition, and a low flow condition. So the pump will be operating somewhere in this range, A, B, C, D. To do that, we need some form of system control, which might be bypassing, might be valve throttling, might be series or parallel pumping, or variable speed. And I'm going to look at a few of those in the next few minutes. The most common system of control is by throttling. You've got a control valve on the discharge of the pump, and you open it or close it to obtain the flow rate you want. And by doing that, what's happening is you are creating system head curves corresponding to the amount of friction in the system. So as you close the valve, you will get system head curves that move up and up like this, and giving you a range of operating points. Here's the same slide, this time with a hooked curve. I hear you gasp audibly. Now, many specifiers will run away, run a mile before they'll specify a hooked curve. They believe they're unstable. They believe they will hunt between 2 operating points here. Will it? The answer is no, it doesn't make any difference. The pump will run just fine. Here is the key thing. The pump is slave to the system, as the pump guru Simon Bradshaw says. It will only operate where the system permits, where the system curve crosses the pump curve. So each of these system curves, as we throttle back the pump, each of them only crosses the pump curve once. So even this point here, people think it will operate, want to hunt between this point and this point. Why would it? The system curve does not go through this point. So unless you throttle it right the way back, and you're well below minimum flow now, you haven't got a system curve that goes there. There is one circumstance at which you could possibly, in theory, get a hunting situation. If you have an extremely flat system curve, so nearly all static head and pressure head, very little friction, then you get a very flat curve. And if you have a very hooked curve, an exaggerated hook curve, then the system curve could possibly cross it twice, and you could get hunting between those 2 points. In practice, you will never, ever see a commercial pump with a curve of that shape. But theoretically, that's what would happen if you did. So another argument, discussion point, do you want a steep curve or a flat curve? Many customer specifications are specifying a 10 to 20% head rise to shutoff as a maximum. And as you saw earlier, that's restricting you to very low specific speed designs of impeller. The question you should be asking yourself is, what are you trying to achieve? What do you want to achieve from the system? Do you want big changes of flow as a result of small changes of system head, or small changes of flow? With a flat pump curve, small changes in system head lead to large changes in flow. With a steep pump curve, the same small changes in system head lead to small changes in flow. Here's a slide some of you will recall from last week's course. Here we see 2 HQ curves, a steep one here in red and a flat one here in blue. Here is the system curve in green, crossing both pump curves at this point here, your nominal duty point. Now, here is the impact of a small change in head on the steep red curve. Here's the new system curve. As you've increased the head by this much, there's the delta H, there's the delta Q, a small change in flow as a result of a small check of this change in delta H. Similarly for the blue, the flat curve. Here's the system curve again, as you've throttled it back, the same delta H, same change in head, this time a much bigger change in flow. Now, if there are differences between the field system head and the predicted system head, by which I mean the total discharge head, differential head that the system is actually demanding rather than that which was calculated at feed stage, well then that change in head will have much less impact on the flow with a steep curve than it will with a shallow curve. They're more forgiving. That is why I favor steep curves over shallow curves, because they're more forgiving. Of course, that's not the only consideration. You have to consider as well pressure of downstream equipment. I realize that. Moving on, variable speed, the answer to a maiden's prayer. Or is it? Not really. This time, the control is the reverse of control by throttling. With control by throttling, we had a family of system curves coming like this. This time, there's just one system curve, and we're changing the pump curve to cross it wherever we want it to cross. Speed change affects pump performance following the affinity laws. Here they are mathematically or arithmetically. And here's what they really mean. Flow changes in direct proportion to the speed change. Developed head changes by the square of the speed change. So if we reduce the speed from 100% to 75%, the flow reduces from 100% to 75%, but the head, developed head, reduces from 100% to 56%. Even a 10% reduction, as shown with this orange curve, 10% reduction leads to an 81%, so a 19% reduction in head. Those who are new to variable speed pumping sometimes expect the pump to be able to achieve reduced flow at the same pressure, at the same head. But unfortunately, that's not how the affinity laws work. So variable speed is not the cure-all that many people expect. Moving on now to parallel flow. Here is the single pump operating curve. And here is the two pumps in parallel curve. What you get with parallel pump operation is the same head will be developed by both pumps operating in parallel. Both give the same head, and the flow they give, well, that depends on their own individual curve. In this particular instance, two identical pumps will share the flow equally. So there is the pump, two pump operating point, 100% flow. One pump will give you 50% of it, the other pump will also give you 50% of it. But one pump operating on its own, if one pump were to trip out, would give you flow at this point. It would follow the system curve. Remember, pumps are stupid. They only follow the system curve. So the system curve crossing at point A, that's the flow you're going to get. Now, it is important that you always check that the one pump operating curve will actually cross the system curve. If it falls short, you could be in trouble should one pump trip. Now, in 40 years in the pump business, I reckon I've received a system curve from the EPC or PMC no more than a dozen times, which is crazy. You should be sending us a curve more often than that. In fact, you should send it to us more often than not, in fact. Anytime you've got a parallel operation sort of situation, you should be sending us a curve so that we can check it. Any pump manufacturer should be able to give you a curve for two or more pumps operating in parallel like this, if you give us the system curve. Here are a couple of slides from my first session, which was on the differences between API 610 12th and 11th editions. It's API 610's recommendations on parallel operation. If parallel operation is specified and the pumps are not individually flow controlled, then the pump head curves shall be continuously rising to shut off, and the head rise from rated point to shutoff shall be at least 10%. I consider that it should be at least 15%. Head values, this is the important part. This is the bit that changed in the 12th edition, and it's a very important point. The head values of the pumps at any given flow within the preferred operating range shall be within 3% of each other. In other words, the pumps have to be closely matching. Here is why this is so important. API 610 allows, and manufacturing procedures demand, manufacturing tolerances. API allows plus or minus 3% TDH change at the rated flow and a little bit more at shutoff. So without this new clause, you could have two supposedly identical pumps, but with a stronger pump and a weaker pump trying to work in parallel. Like this. One stronger pump at plus 3%, the blue curve. One weaker pump at minus 3%, the red curve here. Here is the combined curve. Here is the rated point, shared like that. But here is the typical operating point. If it were operating at this point, which it very well might do, then that is the contribution of the stronger pump, and that is the contribution of the weaker pump. The weaker pump is operating well back at 50% of BEP flow. That pump will be a trouble pump in the future. It'll be short mean time between failure. Now, Simon Bradshaw, the pump guru and my source for this slide, he considers that head rise to shutoff and a continuously rising curve to be of minor importance in parallel operation. Having matching curves is the key. I agree with him, but I would add that in my opinion, the steeper a curve is, the more controllable the pump becomes. Two non-identical pumps can still work in parallel, but you need to control the outlet stream of each pump independently. Otherwise, one pump may well push the other out of its allowable operating range. This is actually the same curve as I showed in the previous slide, but you could consider it for two dissimilar pumps. Again, here is an operating point. Here's the contribution from one. Here's the contribution from the other. There's quite a bit of difference. One possibility of controlling this weaker pump would be to drive it with a VFD to bring the curve up to this point, or conversely, to use a VFD on this one and bring it down. That would improve their chances of working satisfactorily. If you have two dissimilar pumps, I would strongly recommend that you speak to the pump manufacturer or manufacturers, if they're two different manufacturers, to ensure that the pumps can be made to match. This pump, for example, this is the absolute end of operation in parallel. It's the shutoff head of the weaker pump, of pump B. In practice, you couldn't get there. Probably that is about the limit of your operationability, because that's probably the minimum flow of that pump. Go any further back and you'll damage it irreversibly in no time. If the pump was brought up to this speed, then you can operate over a much wider range. Series flow. In this case, The total developed head will be the sum of the heads developed by each pump at any given flow. So you must select a pump to make sure that one pump operating will still make the flow that you require. And here with two pumps operating. Now, if one pump trips, it will fall back down the system curve until you get to this operating point here. So that's the operating point when one pump is operating. That is the operating point when two pumps are operating, and it'll be twice the head. Well, when we get old, we go bald and gray like me, but pumps just get the droop. What'll happen here is a new pump curve, and this is what happens as it ages, as the running clearances wear and open up. You'll get a fall off in performance. But similarly, your system curve will degrade as well. That might be the new system curve, but in an old system curve, you've probably got scale or corrosion in the pipework, and so you get increased frictional losses. So the pump will degrade and you'll get that sort of performance drop off. I can't quantify it because it'll be different on every different installation depending on what you're pumping and the pressures. Every system will be different. I added this slide as an afterthought. You've probably never seen a curve that looks like this. Now, it's an operating near the saddle is an interesting theoretical discussion, but not a likely real-world situation. If you operated with a very, very flat system curve in the region of the saddle, it might cross here like this more than one time, and so you would get hunting between A, B, and C. In practice, it's most unlikely your system curve will be this flat, and you most certainly won't be operating a pump of this size. As I mentioned earlier, this would be a very large pump in the region of 300,000 to 400,000 gallons per minute. You operate those at best efficiency point or plus or minus 10% of them. Note how the head increases dramatically, and indeed the power increases dramatically as you get away from the best efficiency point. This slide just confirms what I've been saying to you just now. Well, this finalizes this part of the session, which brings us to coming attractions. Unfortunately, still not to a cinema near you. You'll have to join us on Zoom. Selecting the right pump for the application. We'll be looking at things such as when to transition from an OH2 to a VB2, when to consider VS6 pumps, barrel versus horizontal split case multi-stage pumps. Thursday, 17th of June, that's 2 weeks today. Again, there will be 2 sessions. One in the morning for the Eastern Hemisphere and one for the Western Hemisphere in the afternoon, my time, morning your time, for those of you in the Americas. We have future plans, which will be for one on NPSH and suction specific speed made simple. Well, simpler anyway, it's not an easy subject. But I would welcome your input as to subjects that you would like us to cover. Okay, I'm going to leave this meeting open for a little while to allow you to post your questions in the Q&A box, and I'll endeavor to answer as many of those that I can now in the next half hour. Those that need a fuller explanation we'll handle by mail in the coming days. Anything that you think of later that you didn't ask now in the Q&A, send us an email at info@rawpumpen.com and we'll address it. So let me have a look at the Q&A and see if anyone has asked us any useful questions. Good question here from Chris Street, who says, sorry, it might be a silly question, but how do you develop a system curve to be able to send out to you? Well, actually, all you need to do is tell us how much is your static lift. In other words, the head, the elevation from A to B, and then tell us also what your process pressure required is. Adding those together, that gives us the fixed component of the differential head, and then from the total head we can work out the system curve. It'll make up the difference. So as long as you can tell us your system pressure and your elevation, the lift from elevation A to elevation B, and we can develop the system curve. Robert Bradford says, why do we need to know specific speed? Is specific speed directly related to head rise? Yes, it is. If the 5 curves I showed towards the beginning of the seminar, they show typically what head rise you can expect for various specific speeds. And there isn't a one size fits all. So the customers who are specifying that thou shalt have 10 to 15% head rise to shut off, that's not the real world. Many pumps have steeper curves than that, and that's what I was trying to show in those curves. Anand Ramdas has said, can you also run a course on developing a pump curve with pumps in service and no service data sheet? I'll need to think about that a little more. Yes, in theory. For example, if you've got an old pump and you haven't got a data sheet or a curve for it, you can develop your own curve by isolating that pump and running it. Take 3 or 4 flow rate points, assuming you can measure the flow rate and measure the discharge pressure from the pump. And from those 2, you can plot an approximate curve. Marco Padilla has said, is it recommendable to control a system with pumps in parallel with throttling valves or with VFD? A VFD can work. What a VFD will do in particular will be to make up for the difference between pump A and pump B, the stronger pump and the weaker pump. With parallel flow, you always get the same head from each pump. So, for example, pump B might be the fixed speed pump, and it determines what the head is that you're going to develop. Now, pump A which is variable speed, the speed will adjust until you get the same head on it as well. So you might well be operating back on the curve with that scenario. It would help if I drew another couple of curves and sent them to you, showing how variable speed on one pump will impact you. Darren Worms has asked, is there a software program available to help with system curve? I believe there are hundreds of them. I haven't actually looked, but there are many that will calculate your frictional losses. You've got to calculate the length of the pipeline, the number of bends, the number of valves and fittings that are in there, and that will calculate how much frictional loss you've got in your system. Question here from an anonymous attendee. How do we receive continuing education credits for this session? If you've registered for the session, I'm not quite sure why you're coming up as an anonymous attendee, but we will send you, if you send us an email to info@royalpumpen.com, we can send you a certificate of attendance for this one. Again, an anonymous attendee saying, wouldn't you need the length of piping to determine friction losses that go into the curve? Yes, that's how you will have calculated your overall system head, or that's how your process engineers will have done so. They'll have taken the length of the pipe, they'll have added in the number of elbows, the number of bends, the number of valves, and then that calculates the total frictional losses in the curve, and that's the job of the process and the mechanical engineer to work on that. Karthik is saying, when the impeller has less opening at exit, for example, 16 millimeters for a diameter of 500 millimeters, the curves are flat. Is it possible to get 10% head rise via new hydraulic design? Yeah, low specific speed pumps have flat curves. That's the nature of the beast. If you have a low flow, high head impeller, it is going to be a flat curve. In the extreme, it will be around about 7 to 10%. It might even be slightly hooked, as I showed in a curve at the beginning. Yeah, that is the nature of a pump of 500 specific speed or lower. To get a steeper curve, you need a higher specific speed pump. Here is one from Dereha Worku. I'm sorry if I've pronounced that wrong. Say, for example, there is a throttling valve in the discharge of a pump and the valve inadvertently opens 100%. Where in the curve will the pump operate? Depends on where the system head is with an open valve. I couldn't say, but the pump will start to climb up its curve until it hits the system head curve. That might be right back at shutoff. It might be at zero flow if there is little friction in the line. Impossible to say with any degree of certainty. Terry House says, how do you account for speed changes within a motor, plus or minus 5% within your system curve? If you've got two identical pumps and two identical motors, they're likely to perform identically. So they will both be running at about the same speed. However, if one pump is not identical and if it's bought a while ago, one of them might be worn and there might be a difference in performance between the two, that will be reflected in the speed that it runs as well. If you've got an old system, old pumps, then I would encourage you periodically to run your own performance test on each of the pumps in that system. And you can do that by isolating one pump and running just the one pump, take 3 or 4 points and measure the flow, the head, and the motor current. And you can then plot a curve for that pump. Do the same for the B pump, and you will be able to see how similar they are and if they are if one of them is more worn than the other. You can also use that as a good way of deciding which one should be the lead pump and the lag pump. So switch them around periodically. How important is suction-specific speed in terms of possible cavitation or erosion at the impeller? We have a couple of OH6 pumps with very high suction-specific speed, values of around 23,000. MPSH margin is about 5 times, but we are still seeing cavitation erosion. Do Ruhrpumpen manufacture OH6 pumps? No, the OH6 pump is very much a special beast. It is the Sundyne pump, the Sunstrand pump. We can do a similar job with a VS6 pump running at much lower speed and having a lower suction specific speed, but it's a complete change to your pipe work and your layout. So unfortunately, it is a specialist beast, the OH6 pump, the Sundyne pump. You need to speak to the manufacturer, get their engineers involved in solving your problem there. Marinella Solar has said, does fluid viscosity affect the system resistance curve? Yes, it does. It's difficult to give a quick 15-second answer to that one. So it's something that I would, I'll give an answer in writing in the next few days. Nehad Hamama, would it be available to run 2 pumps at the start in case we have an issue with the first pump not meeting the system curve? It's a bit of a depends problem, this one. I need to think about it and give you a more considered answer than I can give you right now. Stephen Dixon has said, do you mind to repeat the email address in which to send the certificate request to? Yeah, and any more questions that you do have as well can all be sent to info@ruhrpumpen.com. So info@ruhrpumpen.com. Antonio Zapata has said, how does the use of a discharge orifice located at the pump discharge affect the system curve? Nice question, thank you. And discharge orifice is exactly the same as a partially closed valve. It would be a good idea to use an orifice if you have a permanently changed system curve. Better still would be to change the impeller for one of smaller diameter to allow for the fact that the system head has permanently changed away from what you anticipated. An orifice or a partially closed valve is always going to give you losses. It's wasteful of power, whereas putting the right sized impeller in for the duty, that's the most energy efficient way of doing it. Michael Akinsanya said, at what point do you recommend a diffuser to an impeller? Well, pumps come, maybe I'm misunderstanding the question here, but pumps come in 2 different types. Majority are of a volute design and a minority are of a diffuser design. And so it's a combination of impeller and diffuser in a diffuser design pump, or impeller and volute in a volute designer pump. Well, that appears to be all the questions. I see there are a few chats as well. I'll just have a check and see if if in the chat section people have asked questions. Well, a couple of guys have suggested some topics that I can consider for future ones, so thank you very much for that. One here from Edwin Ling has said, for future topics, could you cover pump safety issues and ways to mitigate? For example, deadheading and water hammer. And Edwin Ling has also suggested that we might consider appurtenances around the pumps. Say for example, okay, so thank you for those. Vimal Engineer has said, can you arrange basic pump fundamental training and a webinar like this? This will probably be best done by your local sales office. It can be tailored to your particular needs. Ones like this, courses like this, tend to be very general, and well, I'm speaking to 115 people right now, so that's an awful lot of people to be able to do specific pump training. So that's probably best done by local sales office, and I'll put them in touch with you. Gerardo Ramos has said, what will happen when the pump operates outside of the curve? What happens with the motor or pump? Well, if the pump operates off to the right of the curve, eventually it will fall off the end of its curve. It will cavitate, it will develop no head. It will cavitate like the devil. The motor power, that will probably drop to zero actually at that point, because you're not pumping anything at all. Exactly how each pump will respond to operating at end of curve will be slightly different in each one, but generally what you're going to see is flow will go up, the head will go down until it disappears off the end of the curve. Cavitation will happen. You'll get, because the NPSH requirement of a pump is generally much higher at run out than it is at best efficiency point. So you will get a lot of noise, a lot of cavitation noise and damage. You want to be able to shut that pump down before it gets there. An example practice for selection of a submersible pump, please. This is from Guillermo Montaño in Mexico. Again, the ideal thing for this would be for us to arrange a training session from your local Ruhr Pumpen sales office, but I will make a note of that. In fact, funnily enough, somebody asked that similar question this morning from our European session. So yes, maybe I ought to look at doing a session on submersible pumps later on. So that's all the chat, and I think we've done all the Q&A. Just looking again, yes, that's all the Q&A. So it just remains for me to say thank you very much for attending today. I've thoroughly enjoyed presenting this and preparing for it as well. I look forward to seeing you all again at the next session, which is the 17th of June, so in 2 weeks' time. Thanks very much, guys. Bye-bye.